Hello, welcome back to the wonderful world of physics. This is the homework for Chapter 8 on gravity. And you can see in on the screen, this is a simulation of planets in orbit around a star. And you notice these are elliptical orbits. And throughout their orbits, energy is conserved. You notice that as a planet moves close to the star, it speeds up. And as it goes far away from the star, it slows down. And so this is a demonstration of the trade-off between potential energy and kinetic energy. When it's closer to the star, potential energy is reduced and kinetic energy is increased. And Johann Kepler actually figured this out. He didn't know about energy, but he figured out the motion of the planets in our own solar system back in the early 1600s, and he was the first to mathematically describe this. Well, let's go on to the homework. Let's start with number 13. To what fraction of its current radius would Earth have to shrink with no change in mass for the gravitational acceleration at its surface to triple? So we're looking at this highly hypothetical example, but it helps us to think through the variables that are involved. So we're looking at Earth. We're thinking about a changing radius. So that tells you there's probably going to be an R0 and an R1. And it says gravitational acceleration is going to change. And we need to think about what mathematical relationship is there between all those different variables. So let's look at what I've written here. We have gravitational acceleration from chapter 8, g, which on Earth is 9.80 meters per second squared. And we get that from the gravitational constant, capital G, times the mass of the planet divided by the radius squared. So I'll say g0 is big G m over r0 squared. And we're looking at the new acceleration, we'll call it g1, equals g, the gravitational universal constant, times the mass over r1 squared. And I haven't put subscripts on big G or m because those are constants. Those are not going to be changing. Now the question is asking about the fraction, how the one G relates to the other. So let's set it up as a fraction, g1 over g0. And so we'll take the expression for g1 and we'll divide it by the expression for g0. So when you divide by fractions, remember, you multiply by the reciprocal. So copy dot flip. And we look at all the things that are going to divide out. The universal gravitational constant and the mass of the planet, they divide out. And what we're left with is r0 squared over r1 squared. And let's consolidate those and call it r0 over r1 squared. All right, so now it says that gravitational acceleration is going to triple. So this g1 over g0 that we just solved for, that is going to be equal to 3. It's a ratio of 3 to 1. So let's set it equal to 3. g1 over g0 is equal to 3, and I'll slip in there what we found in the previous line. g1 over g0 is equal to r0 over r1 squared. So now we're going to not even think about our g's anymore. Let's just cover that up. And we'll bring it down to the next line. We see that r0 over r1 squared equals 3. And we want to solve ultimately for what is r1 as a factor multiplied by r0. And so let's do that. Let's take the square root of both sides of the equation. We get r0 over r1 is square root of 3. And go through the algebra and solve for r1. So as you work your way through it, you get r1 is r0 over square root of 3, which is, you can do that in the calculator, or let's put it in terms of a proper fraction with no radical on the bottom, square root of 3 over 3 times r0. Now, let's get that as a decimal. That's about 58%. So 0.58 times r0. And so what we can do to answer the question, it asks what fraction of the current radius would it have to be? So we can say r1 is 58% of r0. And we drive on to number 15. Two identical lead spheres with their centers 14 centimeters apart attract each other with a 0.25 micronewton force. Find their mass. So the relationship between all these quantities is Newton's equation for gravity. Force is universal gravitational constant, I'll just call that big G, times mass 1 times mass 2 over distance squared. Now, since they are identical, m1 and m2 just become m squared when they're multiplied together. Question says to solve for their masses, so let's solve this equation for m, go through the algebra, and you get that it's square root of force times r squared over g. We're going to plug in these quantities, and we get 8.6 kilograms. Number 17. A sensitive gravimeter is carried to the top of New York's new One World Trade Center, where its reading for the acceleration of gravity is 1.67 millimeters per second squared lower than at street level. Find the building's height. All right, so in this class, we take G to be 9.80 meters per second squared. And we recognize that there is some deviation of that. You go higher in altitude, it goes lower. So if you were to go to the top of Mount Everest, it would be about 9.77. But in this class, we'll just use 9.80. And in this problem, it says that if you go up this certain height, it's going to decrease by just a little bit, 1.67 millimeters per second squared. So we use 9.8 meters per second squared. That would be 9,800 millimeters per second squared. And it's being reduced, that 9,800 millimeters is just being reduced by 1.67. All right, so what do we do with that? It's asking us to find the building's height. What is the difference in heights that's going to cause that wee little bit of difference in acceleration due to gravity? So I'll start by writing what it says in the problem. G at the ground minus G at the top of the building is going to equal that 1.67 times 10 to the negative 3 meters per second squared. And let's think about where we derive G from. It's big G, mass of the Earth, divided by radius of the Earth squared, and that's going to be sitting on the ground, minus big G, big M, divided by, and the denominator is going to be slightly higher than it was at the ground. So we've got GM divided by radius of the Earth plus the extra height of the building squared. And all of that equals what we see at the top, 1.67 times 10 to the negative 3. All we need to do now is the algebra going through the steps it takes to solve for this h that's right in here. So I recommend you stop watching the video at this point and play with it, because you should be able to, at this level, you should be able to take an equation like this and solve for any variable. And this is a bit more complex than we usually get in this class, but you still should be able to do this. But I'll take you through the way I did it. If I want to get h by itself in this equation, I will first divide both sides of the equation by gm. So here I've gotten rid of it, and I've put gm on the bottom. Notice I've written this in a more concise form. Instead of saying 1 over those terms squared, I've just put those terms to the negative 2 power. And I think it's just nicer to look at. If my goal is to solve for h, I want to piece by piece strip things away from h till I've isolated h on the left by itself. So I'll subtract radius of the Earth to the negative 2, subtract it from both sides. Now I've got on the left radius of the Earth plus h to the negative 2. Let's get rid of that negative 2. And that means I am going to put both sides of the equation to the negative 1/2 power. Because if it's to the negative 2 power, I want it to be to the 1 power, to the first power. So I'm going to multiply everything in this equation by, or I'm sorry, not multiply it by, but put it all to the negative 1/2 power, which means square root it and take the reciprocal. So putting the left-hand side to the -1/2 power is easy. It just becomes RE plus H to the first power. The right-hand side, putting it to the -1/2 power, means square rooting it and then taking the reciprocal. So rather than trying to do anything fancy with fractions and how do we take the reciprocal of this thing that involves a fraction, I just write it out a very simple way. Notice I put it in brackets, I put its reciprocal by putting it to the -1, and then I take the square root of it. And it's not the most simplified form. Maybe it is. Some might disagree with that, whether it's the most simplified or not, but it's in a simplified enough form that we're just going to plug everything into the calculator anyway. So when you plug everything into the calculator, you've got the radius of the Earth. You can look that up. You've got minus 1.67 times 10 to the -3. You got your universal constant g. You've got the mass of the Earth. You can look all those things up if you don't know them. And let's be very precise with the answer that we get. This is definitely not a time to take significant figures because the radius of the Earth is 6.37 times 10 to the 6th meters. We're looking for something that's just a wee bit above that, so no time for rounding right here. We should be getting 6.37, I'm sorry, let me not do it in scientific notation, 6,370,000 with an additional 542 meters. And so now when we subtract the radius of the Earth from that, which we're given as 6.37 times 10 to the 6th, we get 542 meters. And I just Google searched what is the height of the One World Trade Center, otherwise known as Freedom Tower. It says 1,776 feet or 541.34 meters, making it the tallest building in the Western Hemisphere. So pretty good result from this problem. Number 19 says find the speed of a satellite in geostationary orbit. Okay, simple enough. We're looking at orbital motion. In example 8.3 in the book, it shows how to find the radius of the orbit for a geostationary orbit. So I recommend you go back and look in your class notes or in the book, example 8.3, and you get this equation, which is also it's Isaac Newton's version of Kepler's third law, this relationship between period squared and when Kepler was talking about it, was the semi-major axis cube. That's going to be the radius of the orbit. And let's solve it for r. R is the cube root, that's my little cube root sign there, of all those things. And so we get that the radius is 4.22 times 10 to the 7th meters. Okay, that was from example 8.3. And by the way, you should be able to produce that result on your own. But now the question is saying to find the speed. And the simplest way to go from there is if we know the radius, we know the period, the speed of something going around in a circle is, remember, speed, most basic is distance divided by time. If it's going around the circle, it's the circumference of the circle, 2 pi r divided by t, and there we go, 3070 meters per second. Number 21, calculate the orbital period of Jupiter's moon Io, which orbits 4.22 times 10 to the 5th kilometers from the planet's center. So that distance it's given is r. It's not saying above the surface of Jupiter, if one can speak of Jupiter having a surface, but it's talking about from the center. So that is r. And it's asking what is the period? Well, no problem. We'll just use Newton's equation, solve it for t, which means in the previous equation, I usually give it to you in the form of t squared equals all those things, but we're solving it for t, so take the square root of both sides. You're going to plug in all those values, and we got the mass of Jupiter. You can look that up, and we get 153,000 seconds. Now, when you've got a number that big, it's useful to give it not in MKS units like seconds, but in something that we can relate to. What exactly is 153,000 seconds? So divide by 3,600, and that gives you 42.5 hours. Or you could divide that by 24 and get 1.77 days. So all three of these answers down below are appropriate. Number 26. A rocket is launched vertically upward from Earth's surface at 5.1 kilometers per second. What is its maximum altitude? This is the type of problem that we might have done in Chapter 2. Basic kinematics, something going straight up, how high will it go to when it reaches a velocity of 0? But we can't use basic kinematics here because that method assumes that gravity is constant. And if you're going this fast and this high, you're going to get far enough away from Earth to where gravity starts to fall off. We can't use g as a constant, lowercase g. And the general rule of thumb, you remember I've said a few times in class and even on this video that 9.8 meters per second squared becomes 9.77 when you get to the top of Mount Everest. And that's like 26,000 feet high. And so that gives you a feel, going above the tops of the mountains, that gives you a feel for, okay, G is starting to fall off. We can probably get away. We're losing a bit of precision, but we can probably get away with still using basic kinematics. But once you start clearing way past the mountains, you can't rely on little g being constant. And this is such a situation. Now, if in doubt, if you're not sure, then use this more complete method. It might be overkill if the thing isn't going that high, but it'll give you better precision. So let's have a diagram here. It's starting with energy 0 right at the surface at a distance from the center of radius of the Earth. It's going up to what height? We don't know what the height is. But when it gets up there and it's got 0 speed, meaning 0 kinetic energy, it will be at its highest. We'll call that E1. Let's use conservation of energy. This is what we worked with in previous chapters as we were learning about energy. Chapter 7 was all about conservation of energy. And here we go. Let's use it. So when the rocket is on the Earth, when it's launching at 5,100 meters per second, it has potential energy, which is negative g, mass of the Earth, mass of the rocket divided by radius of the Earth. It's got kinetic energy, 1/2 mv0 squared, and we're given that v0. Then it slows down, it goes higher, it gains potential energy, and its potential energy is now negative g, big M, little m, over radius of the Earth plus the height. And we're going to go through the algebra and solve for height. And you can see the first thing I've done, get rid of any variables that can be gotten rid of. I'm going to divide the entire equation by little m, the mass of the rocket. At this point, I encourage you to stop the video, stop looking at the screen, and go through the algebra and see how you do, because you should be able, at the level that you're at, mathematically, you should be able to solve for any variable in this equation. And so I recommend stop the video and work it. And I'll talk through it now. So solve for h. The way I approach this is if I want to get that h by itself, I see it's there in the reciprocal. in the denominator. I'm going to take the reciprocal of both sides. No need to do anything fancy with fractions and finding a common denominator. Just write what you've got and put it to the -1 power. That's taking the reciprocal. And on the right-hand side, we have RE plus H. You notice one thing I failed to mention. Look at the top line. It's negative, and it's got a +1/2, and then there's a negative over here. Well, I did a bunch of things. First of all, I got rid of the negative. I multiplied by everything by -1. And so what I've done is I've switched the order of these two terms. Then what I did is this 1/2 v naught squared. I just made that a fraction. I put the 2 down below. Now you don't have to do it this way, but this is the way I'm doing it to make it nice and concise. And then I divided everything by G big M. So the G big M in this term goes away. In this term, it goes down the denominator, and it goes away in this term. And so now the right-hand side is simply radius of the Earth plus h. Finally, I'm going to subtract both sides by going to subtract radius of the Earth from both sides. And I've done a left-right switcheroo, so now I've put h on the left, and there it is. So I've done the algebra, and now it's just a matter of plugging in all the terms. There's the quantities written in green. And we get that h is, and I've broken this up into two separate parts, the bracketed part and the radius of the Earth, just so you can get a feel for how high the rocket has gone relative to the radius of the Earth. So it's up at 8 times 10 to the 6 meters above the center of the Earth, but then we're going to subtract away the radius of the Earth, 6.37 times 10 to the 6, because we want to get just simply how high above the surface it is. So we'll subtract those, and we get 1.67 times 10 to the 6 meters, or 1670 kilometers. And there it is again, 1670 kilometers. By the way, I started this problem saying we used to do problems like this in Chapter 2 with basic kinematics, but you would lose precision, and the higher the rocket goes, the more precision you would lose. So what I'd like to do is let's see what happens if we had used the kinematic method from Chapter 2, which erroneously assumes that gravity is constant. So let's keep little g at 9.8, we could say meters per second squared or newtons per kilogram. And the solution would look like this. Oh, interesting. Okay, so I haven't done kinematic equation. You could have used kinematic equation. I just used the Chapter 7 method of conservation of energy. So on the ground, it's got 1/2 mv naught squared. Up high in the sky, it's mgh. We can divide both m's. Hopefully you remember doing this back in Chapter 7. And you get height is v naught squared over 2g, which is also the result you would get if you had used Chapter 2 method using kinematics. And you get a height of 1330 kilometers. Look how much precision we've lost. The true answer is 1670. Using this method, you only get that the rocket goes up to 1330. And the reason is, in this method, you're assuming that gravity is stronger than it really is. You're assuming that gravity stays at 9.8. And if that were true, it would only get up to 1330 kilometers. But as it goes higher, gravity gets a little weaker. It allows it to go a little higher. And so truly, it'll get up to 1670 kilometers. Number 27 is just added practice, very much like 26. What vertical launch speed is necessary to get a rocket to an altitude of 1100 kilometers? All right, so same thing, we're just solving for a different variable. We are solving for v naught. And so as I wrote, same setup as number 26. If you're confused by any of this, go back to the previous screen, the previous problem, to see how I set up number 26. But here's E naught equals E1. You've got your potential plus kinetic on the surface of the Earth equals potential when it gets up to its highest height. Now is where it differs from problem number 26. Now we're solving for V naught, letting h equal 1.1 times 10 to the 6 meters. So once again, I encourage you, this one should be a little easier than number 26 was. Stop the video, turn off the screen, and solve for h on your own. And I'm sorry, don't solve for h on your own. We are solving for v naught. So solve for v naught on your own. Now, you should be able to follow this. I've added this first term to both sides of the equation, leaving me with 1/2 v naught squared. I multiply both sides by 2, leaving me with v naught squared, and then square root both sides. So in the end, I get v naught equals this, square root of 2gm times the reciprocal of radius of the Earth minus the reciprocal of radius of Earth plus h. And then we plug in all the different quantities, and you should get 4290 meters per second, or 4.29 kilometers per second. Number 44 says, a white dwarf is a collapsed star with roughly the sun's mass compressed into the size of Earth. What would be the orbital speed and the orbital period for a spaceship in orbit just above the surface of a white dwarf? All right, so we're looking at very intense gravity. Just above the surface, that's going to be very, very fast. All right, let's solve this. Mass is the mass of the sun. Radius is the radius of the Earth, and it says we're going to be just above that, so skimming the surface of the white dwarf. And let's go for the simplest equations that go back in the chapter. You get that the speed for something in circular orbit, v is square root of gm over r. And so we're going to get 4.57 times 10 to the 6 meters per second when we plug those values in, and very fast. That's about 1.5% of the speed of light. And if we want to know the period, then we'll use period is the circumference of the circle divided by speed. We already know what speed is, and so we get 2 pi r over v, 8.77 seconds. So imagine a spaceship skimming something like the Earth, the size of the Earth, in orbit and going around the entire Earth-sized sphere in 8.77 seconds, so very fast. You can also solve for t by using Newton's equation for circular orbit. T squared is 4 pi squared r cubed over gm. And there's a bit more to it, but the benefit of using this equation is that it uses just the original information. It does not rely on v. So if you got v wrong and you use the method I used in the black ink here, you'd get t wrong also. So another way you can solve this entire problem is use the equation in the green and solve for t. And then use this equation and solve for v. So you can do it backwards. Number 48 says, satellites A and B are in circular orbits with A 4 times as far from Earth's center as B. How do their orbital periods compare? So usually when we're asked how do two quantities compare, we're looking for a ratio. So we're going to set this up as a ratio between them. And we start with that RA is 4 times RB. That's what's given there. And we can set this up either as a ratio TA over TB or TB over TA. I tend to want to go for, if the problem doesn't specify, the big over the little. And so let's think about which one is going to be a bigger period. And it's going to be the one that's farther away. So that's going to be satellite A. So I'm going to set it up as a ratio of TA over TB. And I'm setting it up as TA over TB squared because that's the format of Newton's formula. So remember, t squared is 4 pi squared r cubed over gm. So not that you need to do that, but I'll just set it up that way in those t squared terms. Look at all the things that divide out. 4 pi squared, gm, all those things divide out. And what we're left with when we clean it up is TA over TB squared equals RA over RB. Notice those are to the third power, so let's put it to the third power. And so the ratio of the period squared is the ratio of the radii cubed. And let's now substitute into that numerator that RA is 4 times RB. The RB's go away, and we're left simply with 4 cubed, which is 64. Now, let's look at the left-hand side and the right-hand side. TA over TB squared is 64, and we want the ratio of TA over TB, so let's square root both sides. TA over TB is the square root of 64, which is 8. So now we have the answer to the question which asked, how do their orbital periods compare? So we can say that the ratio is 8, or we can say that the period of satellite A is 8 times the period of satellite B. Number 53. It says, show that an object released from rest very far from Earth reaches Earth's surface at essentially escape speed. Very far from Earth. Now, when it doesn't specify very far from Earth, what do we do with that? Well, it means so far away that whatever distance, however distance might affect the quantities, it's going to become negligible. So you think as it goes farther and farther away, you get far enough away, and R is infinite. Now, let's just look at what I've done here. So we have E1 and E2, and I've made it starting at E1 far, far away and going down to the surface of the Earth. And by the way, in class, I probably did for you an example of launching something. How fast does it need to go to break away from gravitational effect that the Earth has on it? And it's essentially, how far does it have to go so that it's at zero speed when it's infinite distance away? This problem here is really just the same problem, but in reverse. We're starting it far away at zero speed and crashing it onto the Earth. So I recommend you review that example in class where we found how far does it have to go, or how fast does it need to go? What is its escape velocity? But let's look at this setup. E1 equals E2. At E1, it's got zero kinetic energy, and it's got the potential energy of negative GMM over R1 equals, when it gets to the Earth's surface, comes crashing down, negative GMM over R2, which is the radius of the Earth, plus 1/2 mv2 squared. Let's divide out all the m's. Now, far, far away, let's make R1 a very big number. Let's make it infinite so that that entire term on the left-hand side goes to 0. And if you're uncomfortable with making it infinite, because we can't actually have something an infinite distance away, then you think, let's make it a very, very big number, a trillion, a quadrillion meters, something like that. And you'll see that as you make it a very, very, very big number, make it far across the solar system, you'll see that that term approaches 0. So we're just going to go for the extreme and just make it equal to 0. Equals, I've cleaned up the right-hand side, negative GM over radius of the Earth plus 1/2. I've put in an mv squared. I'll cross that out when I edit it. It should be 1/2 v squared. And then we're going to solve for v. So we get GM over RE. We're going to multiply, get rid of that 1/2 by multiplying everything by 2. We're going to square root. And this, if you'll look back in your class notes or in the book, this is exactly the same. This is the escape speed. If we were launching something from Earth, it's the escape speed. And that's, as I said, because we're just doing that same derivation backwards right here. And here in the green, I've shown you the derivation for escape speed. So you don't even have to review your class notes. I've done it right here. E1 equals E2, and it's going in the other direction. And where we've made the right-hand term, that R2 is equal to infinite, so that right-hand term goes to 0. And if you follow this through, you'll see it's the same, it becomes the same as what we saw for up here. Let's look now at number 62. A satellite is in an elliptical orbit at altitudes ranging from 230 to 890 kilometers. At its highest point, it's moving at 7.23 kilometers per second. How fast is it moving at its lowest point? Okay, so first thing you need to be aware of, when it's telling you those altitudes, it's not giving R. R, remember, is going to be your distance from the center of the Earth. It's not these distances from the center. If it were those distances, 230 kilometers, 890 kilometers, it would be buried underneath the surface. The R that you're looking for is those altitudes plus the radius of the Earth. And so at its lowest point, R1 is 6,370 kilometers plus 230 kilometers. We get 6,600 kilometers. We need that in MKS units, so 6,600 times 10 to the third meters. And we want to solve for V1, that's speed at the lowest point. At the highest point, we're going to do the same, and you should get 7,260 times 10 to the third meters. And we're given that V2 is 7,230 meters per second. There's my diagram right here where I've drawn this center circle is the Earth, and here's the low point at R1, the high point at R2. It's going to be slower at R2, faster at R1. And so if it's faster at R1 at that lower altitude, I do expect it to be faster than V2, 7,230 meters per second. So we'll be able to, when we get the answer, we'll be able to evaluate, is it a bit faster than 7,230 meters per second? All right, let's do it. Conservation of energy, E1 equals E2. You've got your potential plus kinetic at 1 equals potential plus kinetic at 2. Since the mass of the satellite is a factor in every single term, you can divide them all out. We're going to solve through by V1. Once again, I recommend that you turn off the video right now. Don't look at the screen. Solve for V1 on your own. See what you get. And here you can see that what I've gotten for V1. Now, yours might look, if you took my challenge and actually did the solving, yours might look a little different from mine. And that's just because of how we put variables together, how we write it concisely or non-concisely. But the proof of it is if you did it right, then when you plug in all the numbers, you should get the answer that I get. And I get 7950 meters per second, or 7.95 kilometers per second. And we can look and see, yeah, it's a little bit lower in altitude at R1, so it's going to be a little bit faster, and that checks out. Number 64 says a 720 kilogram spacecraft has total energy of negative 0.53 terajoules and is in circular orbit around the sun. Find its orbital radius, find its kinetic energy, and find its speed. All right, so energy, we have mass. It's going around the sun, so we need the mass of the sun. We need the mass of the spacecraft. We've got the energy in joules, so tera is 10 to the 12. And the first question asks, what is the orbital radius? Go back in your notes, go back in the book. This is the equation for the energy of something in circular orbit. We're just going to use that equation, negative g big M little m over 2r. Solve it for r, and we get 9 times 10 to the 10th meters. Question B, what is its kinetic energy? Well, again, if you go back in the notes or in the book, you'll see that in circular orbit, kinetic energy is equal to negative E. Now, that doesn't work for elliptical orbit. Elliptical orbit has a trading off between kinetic and potential. But with a circular orbit, potential stays the same because distance stays the same. So kinetic stays the same, and it is always simply going to be negative E. So it's going to be positive 0.53 times 10 to the 12 joules, or 0.53 terajoules. And once we know kinetic energy, we can answer question C, which is its speed. Kinetic energy is 1/2 mv squared. And so we're going to solve for V. We get square root of 2 times kinetic energy over the mass of the satellite. Plug that in, you get 38.4 kilometers per second. Now we can also check that by remembering another equation. If something's in circular orbit, its speed is the square root of gm over r, or here as you can see, v squared is gm over r. And so we can plug those in and get the speed, and hopefully you get the same answer that you get in problem C. And that is the end of the Chapter 8 homework. I hope you have a great day.